The broadcast is now starting. All attendees are in listen-only mode.
Hello, good afternoon, everyone. My name is Anna Zylik. I'm with ICF, and we are the vendor working on behalf of Energize Connecticut to bring these Passive House trainings to all of you. So thanks for joining. A reminder that we will be recording this training and we will make this available to you all afterwards. And these trainings are at no cost thanks to the sponsors of Energize Connecticut, and we are also in partnership with Connecticut Passive House. Another reminder that the Energize Connecticut program is offering a 50% cost reimbursement for professionals pursuing either FIAS or fee accreditation trainings. So this includes the cost of the training and the exam, and once you become certified, we'll work with you to process the 50% cost reimbursement. If you have any questions, don't hesitate to reach out to us. With that, I will pass it over to Keegan, who's also with ICF, to talk about the Passive House billing incentives.
Thanks, Anna. Yeah, hi, everyone, and welcome back to part 2 of today's continuous installation webinar. Thanks for joining us. So in addition to the training initiative sponsored by the sponsors of Energize Connecticut, they also offer incentives for multifamily buildings with 5 units or more that pursue Passive House certification. So builders, developers, architects, planners should be aware of these incentives for the state of Connecticut for projects that choose to pursue Passive House certification. The incentive structure you can see on the screen divides the incentives. So there's pre-construction incentives for things like feasibility studies and energy modeling, and post-construction incentives for actual Passive House certification. So if you're interested in learning more, do check out the Energize CT website. And we'd be happy to provide you with more information. So with that, I will turn it over again to our special guest speaker, Scott. Hey, Scott.
Hey, Keegan. Thanks for the information and the introduction. Hi, everybody. Thanks for joining us again. If this is your first time, my name is Scott Pusey. I'm a Principal Sustainability Consultant here at Stephen Winter Associates. I'm also a certified Passive House consultant and a Passive House verifier. The bulk of my work is done on sort of the verifier side of the office, out in the field, looking at construction details and helping those project teams get them correct. I work a lot on multifamily construction. This webinar is going to be geared more towards a low-rise, wood frame, single family. So some of that smaller scale construction. But yeah, that's sort of my experience. And we're going to, this is a little bit more about Stephen Winter Associates, what we do. We've got offices in New York, Washington, Norwalk, and most recently Boston. So hi, everybody. Here's some of the learning objectives that we've got for today. They're very similar to what we talked about in the first session of this workshop. We're going to talk more about continuous insulation, specifically on residential projects. Well, we've got a couple of examples of larger scale projects as well, but primarily focused on residential, that low rise and even wood framed projects. But you know, being able to identify those challenging details, talk about some of the approaches of continuous insulation, and then talk about and recognize those innovative insulation components as we get towards the end. In terms of timing for today's talk, it's going to be very similar to what we did last time. Hopefully have a break around 2:50. It might be a little longer after that. We'll take 5 minutes. We do have designated times for questions throughout, but Keegan's going to be keeping an eye on the chat, and please do type in your questions as they come up, and Keegan will try to relay them to me so we can have a little more dialogue, a little more conversational, not quite so lecture-y. One of the things that we do have going on today are some polling, some interactive opportunities for you all to give us some feedback. And so this is through pollev.com. You can see the web address up at the top. And we've already got somebody, thank you, to respond that they are other. We've got 100% other participation so far. If you want to, you can use text to make this work as well, whatever your preference is. We will have a couple of these polls sprinkled throughout. We're going to have a couple of very easy, small, little quizzy type of ones this time around. We didn't have that last time. Some architect friends joining us. Hello. All right. So architects and others, thank you for your responses. We've got one more here. Trying to get a sense of what you are hoping to learn about today. You can link your words with the underscore that's going to come through, and this should give us a little neat little diagram as you all type in what you are trying to hope to learn today. Effective cost strat. Cost effective, I think, is what that is. And then the other one are strategies, installation strategies. Effective construction details, great. We hope that we've got a couple of those. Super high performance details, right on. Common approaches, great. Keep them coming, guys, thank you. Buildability, I like that one. All right, thank you for responding. Here's another slide to sort of summarize why we're here. In terms of pushing the building to be able to be electrified. There are incentives available. Keegan mentioned those at the top. Some of the benefits that we see of doing some of this work and building these kinds of buildings is to really take a bite out of the energy usage and operational cost savings that go along with it. A big benefit is also healthy indoor air quality from these high performance ventilation systems that are part and usually necessary as part of definitely a passive house project, but even you know, high performance projects in general. The ventilation system becomes really very important. Consistent and comfortable room temperatures, as we really do a good job insulating the exterior surfaces, the comfortability of the space really increases. Natural lighting, quieter acoustic conditions, talking here about, you know, more insulation on the exterior wall, perhaps a higher grade window, possibly triple pane really does make it very quiet. When you walk into a passive house sort of for the first time, for me personally, that was one of the first things that I noticed was the acoustic conditions. And a more resilient and comfortable building, all benefits of building this way. So this is part of a three workshop series, and they're broken into 2 parts each. So it's really 6 sessions. We're still on continuous insulation for this second half of continuous insulation. For those of you that joined us the first time, this is going to be a bit of review, but we did want to sort of go through what are high performance buildings. We did kind of talk about this on the previous slide, but the energy reduction, thermal comfort, indoor air quality. I'm not sure if we hit on the carbon emission reduction, but that also, as you build these low load, high performance buildings, really is one of those great benefits. And the municipalities that we work in, as a firm that I work in personally, a lot of these carbon emission things are really becoming kind of a driving force. You know, it's not everywhere in the country, but you know, in some of the bigger metros, Boston, New York, and DC, Philly is right up there. But those first three we see personally quite a bit. These are some of the hallmarks of Passive House. We see Passive House as a great pathway to high performance. I think I described it last time as putting some guardrails around around the design and construction of a high performance building. Passive House is going to insist on thermal insulation continuity, which is what we're really going to talk about today, along with the thermal bridge pre-construction. We've got quite a few, well, we've got a lot of details about thermal bridge construction in the second half of the talk today. Solar control, air tightness. I think if you were to ask somebody who has not quite a lot of experience in Passive House what they know about it, air tightness is going to become top of mind. It is a very airtight enclosure. And then the balanced mechanical ventilation. Continuous insulation generally looks like something like this. This is a basement with you know, pretty thick slab insulation underneath it. It's being shiplapped. It's continuous all the way across. In terms of air tightness, as part of Passive House certification, you need to pass a blower door test. Kind of anything really that is going to be considered high performance in, I think in my mind, and maybe firm wide, would try to be around that 1 air change per hour. Of course, Passive House is going to require that to be much lower. There's two varieties of Passive. It's sort of getting into the weeds a little bit. There's two varieties of Passive House. There's the Theus version, the Passive House Institute US, and then there's the Passive House International Passive House Institute, really. They have slightly different metrics for the air tightness. The balanced ventilation through a heat recovery. So this is an ERV or an HRV. In passive construction, in a certified building, it's going to be running 24 hours a day. The heat exchanger is going to be at least 75% efficient. The ductwork is highly insulated and air sealed, and that ventilator is also quite efficient on its electrical usage, just in what it takes to move the air around the space. Got a brief little pause here if there are any questions about those guardrails for Passive House. And if there aren't any, I'm just going to move on through to some common approaches to insulation. So we wanted to talk about a couple of typical or, you know, options for exterior wall construction. The first one here is sometimes referred to as the perfect wall. As you can see on the deck, on the slide deck here, to my knowledge, this concept was originally coined by Building Science Corp and Joe Steebrook, with a lot of the good work that they do up there in the Boston area. But perfect wall generally referred to in terms of a wood frame. Wood framing is the most common building material, you know, for low to mid-rise buildings. That it's okay for it to be slightly combustible, as opposed to, you know, something in more of a metro that cannot be. Successful wood frame approaches include a couple of different options that we're going to go through on the next few slides. They include Larson trusses, double wall studs, tips, and even 2x6, 2x4, 2x4 in the climate zone. The colder climate zone is not going to quite cut it for, or not even code, but we are going to talk and look about you know, what that might look like with like a zip system, a zip R. So let's move into the Larson truss. And so Larson truss is, as you can see in the slide here, sort of making a very large wall cavity, and it's typically, you know, hung off of, for the lack of a better term, the exterior wall. And some of the layering here is pretty important. And you can see that there's cellulose, quite a bit of cellulose packed into a very large cavity that is outboard of this plywood OSB sheathing. And typically this plywood OSB sheathing, or whatever kind of air barrier material you're going to use, those that becomes the air barrier, right? So you want to tape it with appropriate tapes, and you want to do that prior to putting these trusses on the outside of it. You want to have access to this air barrier layer before the installation, before the thermal control layer is put over top of it. And the thermal control layer is made up of 2x3 exterior trusses. They are gusseted together. These are typically prefabricated before coming onto the site, and then fastened directly through the sheathing and into studs on the inside. So inboard then of this air barrier layer with the OSB, you've got sort of a service cavity that can be used for, it's great for electrical wiring. If you did need to get any plumbing or HVAC, on that wall, it's going to be completely insulated by this very robust thermal layer that is outboard of all of that, as opposed to sort of a more typical construction where insulation would be just in the single cavity that would be shared with all the mechanicals, plumbing, electrical. Don't see a lot of HVAC on exterior walls anymore, but it is a typical practice in some areas of the country. And then of course, cladding, furring strips, everything else that you need to get on the outside of the Larson truss to keep the weather out. You see this in existing buildings can be used as a retrofit option, which is one of the benefits.
Scott, there's a question on the Larson truss, and you may have answered this, but just to reiterate, how is that the Larson truss supported within the wall assembly?
So these are fabricated off-site. The trusses are designed and built to sort of withstand the loads that they need to, right? And the fastening system that is going to get them onto the wall is also, structurally designed. I'm not familiar with a lot of the nitty-gritty details about the structural components of it, but this is kind of I would say, kind of an old school way of doing it. It's been around for a while. A lot of the early adopters trying to do passive building use this method, mostly because it's sort of, I don't want to say low cost. It does use kind of like, traditional materials that are available, in terms of cellulosic wall cavity insulation, and you can get a lot of it on the building. The next one we want to talk about, double stud wall, also right up there with sort of kind of traditional way to approach passive building, in that framing contractors can do this. It's not easy, it's different from conventional framing techniques, but what am I trying to say? All of the things that you need to build this wall are readily available, and if taken from the design stage up, can be implemented without much pain. So see it in single family construction, not so much multifamily. We don't see the Larson in multifamily much either. It's more of a single family application. You can get a very robust, a very thick wall, and so hence the passive house, seeing it on passive homes. It utilizes two separately framed walls to allow for that super insulation. So instead of hanging something off of the structure, it's sort of more integral into the structure, right? Like this is This is all part of the exterior wall and is all holding up your structure. So 2x4 structural stud walls on either side. Well, this one does say 2x3 frame. When I see this, I usually see that it's, you know, two 2x4s on what I've seen in the field. But in this particular, you know, diagram, about 4.5 inches of spacing between the sheathing and then that other stud on the outside. You know, having the air barrier sort of sandwiched in between these two layers is one way to go. I've also seen that this entire cavity is filled, and then the air barrier is going to go on the actual, you know, outside of this double wall. We do have a note here, you know, it can be used in existing building, retrofit, or new construction. I have seen it pretty much exclusively in new construction in my experience. There is quite a bit of framing. We do have that drawback listed as you know, the lumber costs. There is more framing going on here, and you know, the time to build a wall like this is going to be increased. This is usually, you know, site fabricated and stood up on the site from what I've seen. But I think it could be done. I think it could be fabricated off-site, panelized approach. I don't see why not. So specifically now, you know, prefabricated walls, SIPs, structurally insulated panels. This uses a foam insulation, foam component, rather than the cellulose material. So this foam is going to have, in terms of your carbon and your emissions, you know, if you're tracking that for the project, this is going to be a little bit of a ding, as opposed to the other strategies we talked about, where that cellulose is, you know, a wood product and could actually help you on your carbon emission targets for the build. But in terms of operational carbon, you know, the energy moving through this wall, this is something to consider. This definitely can be prefabricated off-site. Most SIPs that I've seen, you know, that is not many SIPs or any that I've seen have been built on-site. So this is a prefabricated option. The insulation goes in between two OSB panels. The exterior would typically be, you know, air sealed as you build it. You know, these joints as they come together with the panels are really quite important to get right. You want to have any gaps or cracks of the insulation layer, you know, filled. Usually a foam gun is on site to be able to do that as you stand up these panels and join them together. But you know, all of the other air sealing that needs to happen is at your typical transition points from the floor to the wall, and from the wall to the ceiling, and then of course any windows or any penetrations. You know, it's all the same. You need to address it on site, all of that sealing. Next one is advanced framing using 2x6. Got a better slide coming up next to talk more about advanced framing, but you know, advanced framing is a way to limit the amount of material that's in the wall and limit the amount of lumber that's in the wall in an effort to mitigate those thermal bridges. And so this one does show, you know, continuous exterior insulation on the outside, which is going to go a long way to mitigating it. But you know, the less framing that you have that is acting as a bridge from inside to outside, the better. The higher the overall sort of the average R value, or more precisely the U value of this wall assembly is going to be, the better that is. a lower U value is more efficient and a higher R value is more efficient. They're inverses of each other. So more about advanced framing. Like we said, reduces the amount of lumber, it optimizes the material, and it reduces the amount of thermal bridging because there just is less framing. Got more slides on this as we get further into the talk today. But an example here would be 2x6 framing, 24 inches on center, doing both a single top and a single bottom plate. The option to have no headers in non-bearing walls, and a single stud at rough openings. Like I said, we've got a couple more slides that we can get more into detail about this. This cutaway does show the rigid foam sheathing, which is going to kind of be your probably first defense against that thermal bridging. But the difference here is this is just a single stud cavity, right? The other options were more of a increasing the size of the cavity on those first two, and then filling the cavity with a really high performing insulation that's got a higher R value than that fibrous material on the first two. Okay, so talking more about building layout as it pertains to being able to deliver a high performance structure and being able to sort of do it cost effectively. The building layout is going to drive some of that decision making, the design choices, and the cost. The complexity of the architecture in the dream build right here is complex, to say the least, right? Taking care to insulate and then also air seal all of those different changes of material, changes in direction is challenging. Something that's a little more, a little more standard in terms of what we see in the U.S. and the Northeast. Even these examples of the layout are going to drive the cost and also the complexity of how you build this. For example, how are you going to insulate this pitched roof, right? It's shown here. We've got 3 stories of living. There's some dormer action going on up front. It looks very pleasing, really pretty from the outside. But how are you going to insulate and then also air seal this? Considerations for probably, I don't know, maybe doing spray foam up here on the sloped roof portion, at least as you get down here into the living space. In the other example, again, dormers, lots of changes of direction, which makes getting that assembly airtight a little difficult. There's going to be some knee walls involved here with all of these various roof lines. Attic knee walls can be difficult to insulate and get those details right. So the point here is simpler lines and geometry are easier for high performance construction, but it's not, we don't need to build boxes. We can insulate these well and air seal them to get them to perform. So talking more about continuous insulation, we talked a lot about walls, but there is also the subslab. This can generally be a little more straightforward, right? A lot of trades are very used to, insulating underneath the slab. It's not anything all that new. What we are looking for in passive building are for the joints to be staggered, to not overlap all at the same spot. Chosen to use tape here to keep everything together and nice and neat. This is also going to go towards helping be a vapor barrier and maybe even a little bit towards having those soil gases stay beneath the slab. Yeah, the foundation piece of a high performance project or a passive project can be pretty manageable. Once we get up to the above grade walls and the roof, that's where it gets a little more interesting. Speaking of below grade walls, these are some of the details we see, you know, overlapping the insulation, right? Like that this piece of insulation is going to run past this piece of insulation. Got a nice way to sort of mitigate that thermal bridge that could possibly happen on the corner if this piece had not been overlapped. So good way to do it.
Scott, we got a question here. I'm going to jump in.
Yeah, go ahead.
So I'll just read it verbatim. When can you replace insulation with sheathing? I've never met a structural engineer who doesn't want to see sheathing directly attached to the studs.
So the question is, when can you replace structural sheathing with insulation? Yes. I don't know exactly when you can. I'm not a structural engineer either. The engineers, you know, are tasked with having that building stand up to all the forces and also meet, you know, the ever-growing amount of code language that is sort of directed at them. So a lot of the examples that we showed sort of incorporated that sheathing into those details, and that is typically what we see on our projects. Is we don't see insulation replacing sheathing. We see sheathing and then insulation together in the same wall assembly. So I know that's not quite what the question was trying to get at, but that's what we see. We're not seeing a trade-off. We're seeing generally both at the same time. We might have some more examples as we get further along. I can't remember off the top of my head though if we do. But now that I know the question's out there, we can address it when we get to them. Talking more about the below grade insulation. There is a transition that's going to happen here from floor to wall, and the slide here is showing, you know, like there's some complexity here in this foundation, and what exactly, you know, is the plan, what's shown in the drawings as to how the insulation is going to run up here, change direction, and then come up to meet. This is the zip R sheathing. We'll talk more about that in detail in a second. But the slide here just sort of showing, like, you know, there's gonna be some transition here, and hopefully it was all sort of accounted for within the construction documents so that nobody needs to, you know, come up with something on the fly in the field to make all of this work. And by work, I mean the insulation from the foundation is going to sort of seamlessly meet the insulation up here at the top. Got another slide showing another transition. And so looking at this, this was a project pursuing passive house. It's sort of a townhouse kind of design. What's circled here is the spray foam that is sealing the mud sill or the bottom plate of that exterior wall to the foundation wall below. And I like this slide because it's a good example of the difference between passive house level of air seal and kind of like a code or even an Energy Star level of air seal. Building an Energy Star home, it would be perfectly acceptable to seal this joint just as they've done here with quite a lot of one-part foam. This is foam that's going to come out of a gun or a spray foam can that you can pick up at Home Depot. In terms of passive house, though, it is not really what we're looking for. We need a higher level of air seal, something that's going to be a little more consistent in its performance. Anytime you use spray foam, and especially the one-part foam, there's the ability to sort of miss spots and sort of like small parts of small gaps, cracks that are within the foam itself, not within the foam itself, but as the foam sort of sets up and does its thing to expand, we found that it doesn't always consistently provide the level of air seal that it looks like you're getting, right? So in passive construction, we would expect to see this to be taped from the zip down to the foundation wall is usually going to need to get hit with some sort of pre-applied, like a primer kind of thing, before any kind of tape is going to be put on here, so that we can ensure that it's going to have good adhesion to the concrete. That's why we talk about change of material, change of direction so frequently within passive building. It's because these types of considerations need to be taken into account. And then additionally, for our purposes today with insulation, right, this insulation is going to get run up, and this one, the blue board is also going to be on top of the zip system. And so, this foam as installed is in the way of doing that. Somebody is probably going to come through here and cut off all of this extra. And again, is that going to really degrade the air sealing properties of how it's installed? In our experience, the answer is yes, it probably will. So yeah, two different levels of air seal, two different levels of consideration there. One passive, and this one sort of showing like a kind of an Energy Star or a code built air sealing detail. Some more above grade transitions. Keep harping on this. It's pretty common to have this foundation wall insulated and then backfilled prior to standing up and starting framing of the rest of the structure. And so remembering to come back and infill this piece with insulation, right? Like that needs to be part of the program, needs to be part of the staging of this job. Zip-R. So we were going to talk a little more about Zip-R, and here it is. Zip-R refers to the zip system that has insulation integrated right into it. So it's an integrated moisture, air, and thermal protection layer all in one sheet. It comes out to the site, it's installed. This is structural. I don't know the level of structural durability that goes along with it. We see it quite a bit. We see it, placed all over the building. And so, of course, check the manufacturer's literature on the limitations of it. But it does come with, sort of a whole system, right? There's the sheathing, there's the tape, there's the sill seal. They've got a liquid flash product that can be used around penetrations and whatnot. And when installed well, it does perform quite well. This is what the Zip-R looks like from the inside and the outside. So you can see here it is a polyisocyanurate foam, and the R value is going to be around R6 per inch. Checking out Zip's website and their literature, you'll be able to hone in on and pick the correct thickness. They have a couple of different options. We see, like down in climate zone 4, the R9 panel has worked on some of the multifamily passive house projects that I've worked on personally. And so, you can kind of dial in the level of thermal control that you want or that your passive house model is demanding. Next slide is about more ZipR. It's a great product that we've been working with, but nothing is bulletproof. You can see here, this outside corner has not been overlapped, right? Those two seams do not join each other. And this is all, this is the insulation that is inboard of the air barrier, the OSB. And so trying to just tape this together as shown is not going to work. The tape wants to overlap any seams by, I think it's about 1.5 inches, 2 inches, maybe even be more. But even a wider piece of tape is not going to bridge this gap. And even if you did try to do that, there's no structure behind there. Anything that's going to come up against the tape then is going to put a hole in your tape, right? Like if you just try to tape it. So something needs to be infilled here to sort of correct for the fact that they did not run one piece of the sheathing out to actually form the full corner, form a structural corner. So a little bit of a miss there. Okay, so what other kinds of exterior wall stuff have we seen or is out there? Some other options to consider. Exterior XPS with furring strips, exactly as advertised here. So in this case, they chose to use the zip system as their air barrier and then cover it with 4 inches of Dow styrofoam. So that's the XPS product, R5 per inch. So a very robust wall assembly, a lot of insulation on there at 4 inches. And you can see that they're going to be using furring strips as they go up. I've got a better shot here. This is, I believe, the same project, but using those furring strips to sort of fasten the insulation to the structure, and then all of this having been worked out by structural to determine what the spacing is of the lath, and then also the screw pattern, so that you can hang whatever you want to hang off of this. I think it was probably a cement siding on this one. Here's more of it, more of the furring strip stuff. So yeah, kind of a straightforward way to go about it, but not quite as straightforward as getting just one sheet good out there and delivered with all of your insulation in one spot. It can go up quite a bit faster from what we've seen, because you're still in this situation, you're still needing to do all of the sealing with the tape and whatnot, and then there is sort of the extra labor to come back and get the thermal control layer on top of it. Another option for mineral would be to use mineral wool. We talked about mineral wool a little bit during the last talk, and I think we had a question about sort of fastening it to the building, and so I found this slide from one of the manufacturers, showing some of the typical pin placement, some of the fastening options that you have. So there's the plastic nail caps, you've got metal fasteners, you can use wood screws with something else along with it. Along the right side here of the graphic, sort of more of the clip systems that you might see, clip and Z-girt. So I think I mentioned Cascadia clips the last time, but here it is again. Cascadia being an example of a thermally broken clip. It's made out of, I think it's fiberglass. And so it's going to be able to attach to the structure of the building, either concrete or sometimes a steel frame. There's going to be insulation in between all of it, and then this clip is not metal. It's not going to be all that conductive, and so the insulation layer is a little more continuous in terms of being thermal bridge free. And then there's some other options here with brick ties and wedges and all that sort of stuff. So the options are out there, and manufacturers have want to sell you the product. They've got solutions to be able to make it happen in terms of mitigating those thermal bridges and getting the material to stay on the wall. Sort of kind of a variation on the theme in terms of like a lath. This actually was a passive project. You can see, a CMU backup wall. We've got wood lath that has been attached, screwed onto that masonry. This wood lath is acting as a little bit of well, it's not bad. It's a pretty good thermal. It's not as bad as the metal that needed to be used to get this insulation in place. And so this was not how this wall assembly was originally designed in the construction documents. It's a little bit of a compromise. There was an actual RFI that went out during the project, and we were asked as the passive house consultant to analyze it, to take a look at it, to do some, I think we actually did some therm modeling on this, trying to really be very specific about how much energy was going to move through this wall assembly. And this is just at the stair towers of this building. There were only 2 stair towers on this 3-story. I think there were 60 apartments in this project. And so the construction type here, this would not have worked for the entire, the entire above grade wall assembly, but it did pencil out okay for, sort of like a limited application where we needed to have this CMU wall, for the stair tower construction. So again, the wood studs are acting a little bit as a thermal bridge, or as a thermal break, to keep the actual metal off of that wall. But again, the insulation is still being shown in between the metal. So it's not great, but it did pass on this particular build for these small wall sections. It did pass passive house muster. It was able to work. So we're going to move on to sort of some more about bats, more about fiberglass bats from the inside, from the interior. See a lot of fiberglass in the work we do, even in passive construction. There's probably always going to be a place for that fiberglass cavity insulation. And so I think we've got a little video here. Hopefully it works. So this is a little mock-up that we had built for some training purposes, but you'll see my colleague here, Mike, demonstrating how mineral wool is, installed sort of perfectly. You can see that that electrical outlet was pre-cut, right? And then the insulation fitted in. Now he's working around and, having pre-cut and now cutting again around that MC cable so that the insulation can sort of wrap around it and not be compressed by the electrical wiring. You can see that it is all, pretty much perfectly cut to fit, and you end up with, at the end, a really nice looking install with everything fitting all pretty much perfectly together. And so that's what we would be hoping for in any cavity insulation install. That's sort of like perfect finished with no gaps, no cracks, no compression. You know, that's a very small section of wall that he did, but kind of what the goal is, right? We talked a lot about this in the previous one. We're going to talk about it in the previous talk. We're going to talk about it a little more. So this refers to the ResNet protocol, ResNet Residential Energy Services Network. Got some insulation grading, and so the one here to the right, or sorry, to the left, grade 1, no gaps, no cracks, you know, near perfect. So the one, the video we just watched was a grade 1. Grade 2, you're allowed up to 2%. Grade 3 is 2 to 5% in terms of compression, or, well, yeah, compression and small gaps. So this is going to become another interactive opportunity for everybody. Wondering what you all think about this insulation install and what kind of grading you would give it. So again, these are the grading options, and I'll switch back and forth. Almost no gaps. Is it grade 2? There's 2% worth of gaps. Do we think it's grade 3, where it is 2 to 5%? So please text your answer. All right, so A, B, and C. Got some more votes for 1. Give you all an opportunity to sort of chime in here. I think as I click back that we won't lose the results, but 25. All right, so the votes for grade 2, 44%. Here's what we were asking you to grade. And so, yeah, good. So the results stay. Great. 33, 44, 22. So in looking back at it, in my opinion here, I see somewhere between a grade 2 and a grade 3. I don't think grade 1 is really warranted because, you know, there's quite a lot, especially along the bottom here. These bats were not cut to fit. You can see, especially here, this bat is overstuffed, and you can see on the next one it's overstuffed. It's too big for that cavity. Telltale sign is that it is tucked under. If you were to untuck it, it's going to fall all the way down. You know, you can see this is just too much insulation material. And then down here, a lot of compression, all due to being too big for that particular cavity. You can see along the stud wall here, along the studs, you can see quite a bit of framing. If this were grade 1, you would really just see the face of the stud. And so, yeah, I'm going to call these first couple of cavities here maybe would be a grade 2. But in looking at a lot of this, I think it's close to, but I think it's kind of on the line between 2 and 3. Another one. In grading, example 2. What do you think about this? I know it's not a very large section of wall, but that is something to sort of take into account when you're looking. The grading is written that, you know, you're looking at a section of wall and you want to sort of kind of in your mind average across it. The cutoff for grade 2, again, is no more than 2% of what you're looking at is gaps. Somebody has already feels strongly that it is grade 3. Thank you for the quick response. And so same rating system, text A for grade 1, B for grade 2, C for grade 3. That's what we're evaluating here. Yeah, I don't know how many people voted, but it looks like everybody is saying this is a grade C. I would agree, especially this image right here. They did not cut around around the electrical outlet. It's pretty obvious how squished together everything is, and then this bottom one, this bottom bat is maybe twice the size that it should be. I'm not really sure, but is really kind of thrown in there and squished in there. So yeah, I would say a grade 3. Next one, grading example. I think you're sort of getting what we're going after here. So the opportunity to vote again. Oh, I think we've got it should be grade 3. It says grade 2, but yeah, everybody gets the picture. Yep, and I would agree. I think it is a grade C. There's not much insulation here that I can see. This is kind of bordering on like it's just missing insulation, perhaps. But yeah, this stuff is really very overstuffed. How about this one? This example. Get much larger wall section here. Got some spray foam incorporated. Wondering what your thoughts are on that. Grade 1. A couple folks for grade 2. All right, so 70-30-ish. Let's look at the image again together. I see up here at the top these blockers across the header. Yeah, those are not necessarily grade 1. On the whole, though, on balance, there is it more than 2% of the wall area that has any compression? I don't know. I think you could kind of make the argument that it is very close to grade 1, just given the overall amount of area that we're looking at and the percentages that we're trying to hit, right? So it can be up to 2% of gaps and still be a grade 2. So it's close. My feedback that I would typically give anybody on site as I'm sort of doing my inspection here would be to, redo or, cut and fluff some of the blockers up here, and then you definitely have a grade 1. Thanks for your participating in the poll, everybody. Spray foam. Spray foam is another way to fill a cavity with a thermal control layer with insulation, right? You got to get the measurement. This example here is a open cell spray foam. I can tell because it looks like it was pretty easily shaved off any overspray, and nice and neat. The grading of spray foam is usually pretty straightforward, especially when you get stuff that looks like this or like this, right? Like that insulation is fully filling the cavity. It's not compressed. It can't really be compressed. And so, you would kind of have no other option but to call this grade 1. Now, that's not to say that foam is infallible. You want to get up close and personal when you do evaluate what this looks like on your projects. Rim joist area is a great spot to use it. But there can be a lot of sort of hidden imperfections, not so much in terms of the thermal properties of it, but if you are relying on this as an air seal, we talked about it a little bit last time, all of these sort of like imperfections and sort of holes and whatnot are the opportunity for air leakage to happen if there's not a good air barrier on the other side of it. Some more examples of what, the rim joist insulation can look like. Again, I would call this a grade 1 install, but in terms of air sealing with spray foam, you got to really be careful, and my recommendation would be to use a blower door and do some evaluation to determine if it is in fact as good as it looks, because it can be obscured a little bit, the air sealing properties. All right, so more insulation. Now moving to the roof, to the flat roof example. This is can be pretty straightforward for a flat roof. Kind of similar to slabs. Keegan, was there another question?
Yep, Scott, sorry, yeah, just on the last one there, I think someone was trying to confirm, were the multi-stud joints there caulked?
Oh, yeah, here. Yeah, so that's a good question. And to my eye, it does not look like it was caulked, but it's a great question for, your air barrier strategy, right? I think I had another image a little further back. There's some caulking, right? Like those studs have definitely not been caulked. So the question is, do they need to be? And the answer is, it depends. It depends on what the strategy is, right? A lot of this interior caulking, caulking the sheathing to the framing members, that can be pretty effective. It's sort of a throwback to when the exterior air barriers were not quite as robust. The zip system generally is going to work really very well with the tape that is applied to the outside. Caulking, sheathing, and whatnot to the inside when you're using zip system is kind of a belt and suspenders approach. If you didn't have zip system, if you had some other kind of air barrier on the outside, let's say like a Tyvek product, right? Like something that is not kind of fully adhered to the outside of the wall, then yeah, using this belt and suspenders approach, yeah, definitely going to want to do that if you're trying to achieve a really very well air sealed project. So it's there, and the reason for that, you can see that as you caulk across from the inside, typically referred to as like picture framing these studs. Every time the stud interrupts your air seal is an opportunity for leakage, and they're trying to mitigate that here by running the caulk all the way down both sides of the stud. It's just a lot. You're kind of introducing more surface area into your air sealing strategy. The better strategy, and especially for passive house, is to have the air barrier all be in one spot and do a really good job having the air barrier at that location, right? So with this zip system, the air barrier should be on the outside. All those joints that are being taped and sealed together should be doing, the heavy lifting of keeping the air out. But again, kind of like a belt and suspenders kind of thing. So back to the question, like, was this sealed down the middle? No, I don't think it was. But you got to go back to sort of like the design intent. Does it need to be? And the answer is no, not always. It depends on what the strategy was. But yeah, I have been trying to tell my teams that are doing this, like, there is one air barrier on the project, and we need to do a really good job making sure that that air barrier is all connected to each other, and the transition points are done well. And if that's the case, then you don't need to sort of do the interior portion. You know, you don't need to seal on both sides of your zip sheathing because you've done such a good job on the outside. The roof insulation, the flat roof, it's pretty straightforward. There's not much to say here. You know, overlap the joints. Guys have been doing this forever, overlapping the joints. If you can't get them to butt together very nicely, have some spray foam, some of that canned foam on hand so that you can get the joints. Anything over 1/4 inch needs to be foamed, even if you are doing sort of a shiplap type of deal. And, you know, sort of to that point, you know, some of this insulation material can get pretty beat up, right? So as you join these two joints together, they're not going to be perfect, and you're probably going to want to spray foam those together. Here's an example of what polyiso might look like on a sloped roof situation, right? So there's some lap here that's sort of separating the insulation underneath it from the roof deck that is above. There's also a roof deck below. And so, you know, you can introduce some sheets of insulation to even sloped roof assemblies. You just need to get it designed correctly. That, you know, usually what we see is kind of a small ventilated shaft, which is what we've got going on here. And here's more about roofs being insulated, sloped roofs. See a lot of spray foam in this situation. Again, it's there for the thermal continuity, not so much for the air sealing. I think we shared these images the last time we were on. You know, beware if you're trying to use it for air sealing as well. It does a great job for thermally, but the air sealing can be a little deceptive. Here's some more flat roof sealing insulation being done with spray foam. And then I think this is our last slide before the break, but we started to see some interesting, you know, signs and notices. As you can see here, this one is pertaining to both the thermal and air control systems of the building. And, you know, these systems are integral to the design, and, you know, nobody wants to have to go back and keep fixing and keep touching it up, especially on large projects where it's very easy to lose track of, you know, where penetrations were added after the air barrier system was completed. QC can become really critical here from contractors to, you know, really remain very vigilant as to, you know, the integrity of the air barrier, the integrity of the insulation barrier. So I think, yep, we're going to come to our 5-minute break. If there are any questions, please let Keegan know, and we'll get to him afterwards, after the break. So we'll say it's 3:10. Let's everybody come back at 3:15, and I think we'll be done right on time. We don't have quite as many slides in the second half. So 3:15, everybody. Thanks. All right, everybody, welcome back. We're going to talk in the second half a little bit more about some innovative insulation components, as the slide says here. Keegan, let me know if there were any questions that came up.
Yeah, we
before
have
the break.
Yeah, we had one I wanted to have you answer. Is there is there UL testing for roof systems that have the additional insulation on the roof assemblies?
I'm not sure. We don't get into a lot of the UL testing in the work that we're doing. We're sort of evaluating the thermal properties, like, you know, in layers in a lot of the software that we use. And but no, I don't know the answer to that. Sorry. So let's talk about continuous insulation in terms of like defining it. From ASHRAE, found this definition and, you know, agree with it quite a bit, but it's uncompressed and continuous. So we just talked a lot about, you know, compressed and sort of like, you know, not so great insulation, but it's across all structural members without thermal bridges other than fasteners and service openings. So a service opening would be, you know, ductwork, a ventilation fan, anything that needs to sort of penetrate that, I would count as a service opening. Guess you could also maybe, I wonder if windows and doors would be included in that as well. I don't know. But anyway, it's installed in the exterior or the interior, or is integral to any opaque surface of the building envelope. So integral, you know, zip would be an example of that. You know, right into the opaque assembly. But this is kind of the definition of continuous insulation that we like. Another option here for some response from you all. What types of thermal mitigation strategies have you seen implemented on your projects? You can use that underscore to link them together. But what have you all seen used? Okay, that's framing. Anybody else with wanting to chime in? Done. So continuous insulation, yeah, we see quite a bit of that. But all right, definitely showed this slide during the last talk. Got it again here. It's kind of one of our favorites in terms of the thermal bridging and kind of putting it into a visual context, right? If you move all of that framing over to one side, as the graphic shows, the wood's going to represent up to 25% of the wall surface. So that's definitely without advanced framing. That's sort of like traditional framing. And then here's another way to sort of evaluate that. And this is from Hammer in Hand. The example here is an R50 wall with 25% wood framing. So in a given 10 by 10, so 20 square feet of wall, just doing the math there and doing some of the heat loss calculations to say that, you know, the thermal bridge of the wood, this is assuming that, you know, there's no continuous exterior insulation on the outside of this, you know, wood. I think that's true. The R15 for 25 square feet. No. At R15 for for wood, there is some insulation on the outside. Anyway, even given that, right, the R50 wall, the thing to take away from this slide, you think you're getting an R50 wall because there's R50 cellulose insulation in the wall cavities. In reality, you're left with an R32 after you take the wood that is in the wall into account. And so not quite half, but it's quite we would call this typically derating the wall assembly to account for the wood framing. And so if you're doing passive house, even if you're doing, you know, Energy Star or sort of a HERS methodology, anytime you build your wall assembly in that software, it's going to account for this sort of derating of the wall assembly based on your assembly. And so that's why in passive construction, we see, you know, beefier assemblies, more thermally broken assemblies to really mitigate this drop off in performance, right? The amount of energy that's moving across this enclosure, across this assembly. Here's another way to look at the thermal bridging and how to mitigate it. Here's some of the strategies. We've already talked a lot about them. We're going to talk more about sort of some examples and details, but you know, that thermal, this here is, you know, breaking the thermal bridge using the 1 inch of rigid foam, and you know, just how effective that can be. Another way to look at advanced framing, got a couple more slides on this. The advanced framing is shown, you know, in the darker color, in the wood color. So I see ladder blocking not just for thermal continuity, but also to save some material, right, for drywall nailers, not having to use a full piece of lumber all the way down, you know, to give the drywall something to fasten to. But in this context, thinking about being able to get insulation around these framing members in a more continuous manner. So the conventional framing is all shown in yellow, and then the advanced / conventional framing shown in the hashed. So an example here, the conventional framing is certainly going to have a double top plate. And if you're going to do an advanced framing, you could possibly get away with a single top plate. To be honest, I haven't seen that level of advanced framing in practice, mostly because, you know, I'm seeing a lot of multifamily construction where you know, the structural engineer that they need this. The building needs, you know, more a beefier construction to do what it needs to do. Here's some other advanced framing options, talking about the headers and double ply headers, leaving room for the insulation. Got a slide that's going to show that a little bit better. The corners are a good way to do it. This sort of shows the ability to perhaps line up the framing from top to bottom and take full advantage of that structural, being able to take some of the load off of the top and bottom plates. You know, maybe if you are lining that sort of stuff up, as well as the trusses up above, you might be able to get away with that single top plate. This is all shown in 2x6 wall, 2x6 wood. And then again, you know, the sheathing on the outside, to the question asked earlier, it is important. It does play a large role in the structural stability of the building. And so, again, we don't see a lot of actual structural sheathing being replaced with just insulation. It's just not something that we see very often. not to beat a dead horse, but here's some more examples of what it might look like. Here's an example of ladder framing. A raised heel truss is considered advanced framing, where you raise the slope of your roof up using this heel, and then you can get more insulation to cover your exterior wall below. The corners, kind of a good example of what this diagram is going to look like in the field once it's framed up. And you can just see that the amount of insulation is much more effective just by turning this piece of framing the other way and backing it in. You can mitigate a bit that thermal bridge. A newer material on the market called the T-stud uses 2 lumber members and an internal truss system. There's 2 varieties of this. There's sort of the T-stud with an R19. The next one is the T-stud called Bare Naked in their information. The difference here being what sort of comes from the manufacturer in terms of the fill. So this is shown with a closed cell foam. It's going to help to really reduce the thermal bridge caused by the framing, caused by the studs. So there is 24 inches on center with a wind load of 1 through 5. To be honest, I don't really know. I don't know exactly what that means, but the point here that it is a little, even at 24 inches on center, you're going to be able to achieve some of the wind load requirements. And there's sound transmission reduction as well. Let's look at the Bare Naked one. So this one, Keegan, go ahead.
Oh, yeah. Hey, question. Have you run into removing most headers by the use of structural rim boards?
Oh, interesting. No, I haven't seen that in practice. But yeah, let's go back and talk about that. So the rim board here is largely a function of just, kind of covering the floor cavity, right? But I think what the question is getting at is there's some other newer material on the market that could possibly take some of that structural load and thereby negating the need for some of the headers below, because the load is being transferred down to the rim board. The rim board has some structural properties. It's dispersing that load, and it's going to carry it across the opening there. But I haven't seen it in practice, to be honest. I don't know that I've seen a sort of a cut sheet of it either. So I kind of want to look into that and see if we can include that in the next talk we do. So thanks for the note. Yeah, here's where we left off, the T-stud. So this is the Bare Naked version, sort of, can be insulated. It's sort of a double wall kind of, methodology here, where these dowels that are between the pieces of framing, the stud comes out all together, right? And now you have the ability to get insulation in between there. And so instead of the full length of the stud acting as the thermal bridge, now it's just these couple of pieces of dowel that are doing any transmitting. And when you can work insulation in between and around any kind of framing member, it's going to reduce the amount of thermal bridging quite a bit. So bone-in fiberglass cellulose, spray foam, great options to use here. In my opinion, using a fiberglass bat is not going to deliver the full bang for the buck in terms of mitigating the thermal bridge, because it's going to be difficult to sort of work that bat that insulation in between here without really, degrading the R value of that fiberglass batt. So that's the way we talk about here blown-in options. You can blow in mineral wool, and of course, spray foam is a blown product. Here's a little more about headers. This express header is an option that might be available and applicable for some projects. Sort of, right off the shelf, right out of the catalog, we'll be able to deliver an insulated header. Of course, it's got to be sized and whatnot for what you need. But you can see a couple of the different options over here: 2x4, 2x6 construction. Looks like there's an LVL option as well as, well, no, it's all LVL construction. So you get a 1/4-inch LVL, 3 inches of expanded foam for the 2x6 construction, and then another piece of laminated plywood there. So that's pretty cool. You don't have to build your own one on site. Other ways of looking at the continuous exterior insulations is mineral wool product being shown. It's a rock wool product. You can see the fasteners that were used here. And so 4 fasteners on this side here. This sort of fuller batt is using the 5. If I remember correctly, that's what we were looking at, the 5 fasteners in the previous slide where we talked about fastening mineral wool to the outside of the building. And it's a nice way to do the cuts here and the offsets to be able to get those corners to work really well, is to leave some run, and so that you can infill with your next piece below and sort of stagger that joint as you go up. I think we've got a video of somebody doing that later. Furring strips over continuous rigid insulation. This one is a polyiso insulation. Yeah, Hammer and Hand even has some steps on how you want to sequence this operation. So with this one, these fasteners are going right through the lath, through the continuous insulation that is behind it. There is no gap. There's no it's all one piece of insulation through there. And so fasten furring screws, spacing and fasteners are decided by the weight of the siding and the material. But, probably they're going to be hitting interior studs. Not all the time. It could be hitting, the plywood or whatever the substrate is behind it. It all depends on the rest of the assembly. Here's another mineral wool insulation way of doing it, using sort of the lath again, holding that mineral wool in place. And so you can see there's a couple of fasteners that have been placed there. I think that's probably just to hold it in place while the rest of the assembly gets constructed. Yeah, nails or screws with washers, and then you can do a second layer of mineral wool depending on what how big of a R value you want, and using the lath to sort of hold it all in place, and then also giving the rest of your wall something to hang off of, to be fastened to. Here's more of clip and rail. This is taken directly from Cascadia's website. You can see that clip. It's the clip is made out of steel, but the Cascadia part here is sort of thermally breaking that. It's isolating that steel that would otherwise be a very good conductor of heat, very good conductor of energy, a really big thermal bridge. It's being mitigated by the fact that this piece of material right here is not conductive right? It's not allowing that energy to transfer. And so here you can see a slightly different variety of that. This is another clip system, clip and rail, typically referred to. And so this furring, it looks like a Z-girt. It's probably metal. Is being held off, and sort of very similar to like what the T-stud kind of approach is, being able to get insulation around this thermally broken piece of material is going a long way towards improving the overall effectiveness of this wall. Porches and balconies definitely should slide the last time, but it's important to bring up again in that, there are porches, there's balconies, there's stuff that gets fastened to the side of the building. You need to make sure that you've got something to mitigate the thermal bridge caused by having the piece of this ledger board screwed directly onto the building, right? And so 1-inch high density foam has been spec'd to go between those two pieces of framing, and it's helping you to continue that continuous insulation. You can see here in the detail, it's not to the same depth as the rest of the wall, but it's something. It's 1 inch, and it's going to create that thermal bridge or that thermal break and mitigate the thermal bridge, which is what we're looking for. And for this ledger board going all the way across, the 1 inch is going to satisfy what you need structurally and also provide the thermal break. So some other thermal breaks. Armatherm is another commercially available product out there. It is a high strength closed cell polyurethane material. There's a couple of different densities that it comes in, and you can see the specifications table below. You can see as the compressive strength goes up, the R value per inch goes down, but out here at the 2,150 PSI, the strength, roughly an R2, it's a little bit of a thermal break, not much. And this is definitely more of like a high-end product that we're going to see on some heavier constructions. Got some pictures of where we might see this. This was from I think this was like a 7-story tower that this piece of Armatherm was being spec'd. This is the footer below. There's a concrete topping slab above this insulation layer, and then the Armatherm being specified as a thermal break between the steel beam, steel post above, and the cold footer and slab below. So trying to mitigate that thermal bridge with this piece of Armatherm. You can see it's the 500 to 280. So it needed to be sized with quite a bit of compressive strength. And so it's an R2, better than an R0. Here's some other examples of when we see this in some of the heavier construction. It's going to support roof equipment in this case. See several blocks stacked up on top of each other. With the, this is then going to be infilled around it with the roof insulation, a flat roof insulation, going to be filled around it. Here's some other examples of what it's going to look like. This dunnage on top, again, being sized to match the roof insulation. You can see also even the roof curves for setting, this is probably going to be like some outside units for mini splits or something like that. So those are being thermally broken from the roof structure below. You can see there's quite a few of them here on this particular roof, which is, probably what is necessitating the need for this much arm therm up here. You usually see it being used pretty sparingly. It is pretty pricey. What are some other options for thermal breaks? This is, again, a little more like a heavier construction, but what you're seeing here is a section at a balcony. And so this is a concrete deck. This is the balcony door up above. And so this is the balcony as it, is on the outside. Here is the interior. And so this particular system was an EFIS cladding, 4 inches rigid insulation. But what we wanted to show here is this particular brand. It's a German brand. Shoot, blanking on the name. I'm going to have to look it up. I'm going to look it up and see if I can find it. But this is what the system looks like in a cut sheet. Here's what it looks like installed. I think that's just wood framing on top of it. It might be Armatherm. I think it's wood framing. This wasn't my particular project. But anyway, you can see that this material here is acting as the thermal break. It has insulation in between it, but what it's doing is it's tying the structure from the balcony into the floor system towards the interior with all of the rebar that's going through it. Now, I know that it's a lot of rebar shown here. There's a lot of rebar in the picture. It's still better than just a regular old, kind of conventional way of doing this, which would be to, have a lintel or some kind of like big thing of steel in here to be able to hold them together, or even if it's, poured all as one mono slab. This is a better solution in terms of breaking the thermal bridge created by that would be normally created by the concrete between two things. So again, this is a balcony example. EFIS insulation. So typically expanded polystyrene, EPS, that's different from XPS, which is extruded polystyrene. EPS is the coffee cup white material. It's used very frequently in an EFIS system because it's a lot easier to shape. It's a lot easier to sort of get the finish to be, without a lot of bumps and warping and that sort of thing. It's, this is the finish of the building. And so using EPS insulation is preferred. XPS insulation is much harder to shave and sort of shape to get to be, for it to look good from the outside. What we wanted to mention here was this graphite polystyrene. So it's small pockets of air within a polymer mixture, and then the graphite has some other thermal properties to sort of reflect that radiant heat, similar to like a low E coating on a piece of glass or a window. So the R value is slightly better. It's R3.85 would be the EPS, the regular coffee. This is a 4.7 per inch. And so when you're fighting for sort of every inch of building material or inch of insulation, this could be an option to consider when you want to use an EFIS finish and get that higher R value to meet your project requirements. To meet the passive house model, to save on space, the width of your exterior wall assembly. This is an option. Here's an example of what parapet insulation might look like when it's wrapped with some mineral wool. And so you can see the actual capping of the parapet going on over here. This insulation has been held on with a combination of I think those are screws with the cap, and the rail here is also helping to hold it on. It's not like a great install down here with a lot of, it's not very contiguous, you know, it doesn't look very pretty, but you know, it can be done using mineral wool to wrap the parapet. Of course, all of the air sealing and everything would have been done underneath it as well. Got another short little video here. Only got about 5 more slides to go. So this is another example of mineral wool insulation done from the outside. And what we wanted to show here was this concept of insulating over the frame of a window. This is not something that we see a whole lot of, especially on a lot of the multifamily projects we work on. Single family, it might be a little more typical. And what they're trying to do here is to get the R value of this mineral wool insulation to sort of overcome any deficiencies in the frame of this window. So sort of increasing the R value of the window frame is a way to sort of mitigate the thermal bridge being caused by the window itself, typically referred to as over insulation. So that's, I lied, I don't have 5 more slides. I've got 1 more slide, 1 more poll. It is 3:47. Thanks everybody for sticking with me and sticking with us as we went through some of these different insulation options. I hope it was helpful. I'm wondering if you have any final thoughts or takeaways from the presentation today. Feedback would be appreciated. I know there's a survey that will be sent out later. Any feedback would be appreciated so we can you know, improve this training for the next round. Oh, good. Yeah, thanks. Glad it was helpful. Hope the information was helpful. So yeah, thank you everybody. We're going to be providing some PDF version of the presentation. Obviously the videos won't be included in there, but we'll be providing that. And thanks everybody. Keegan, were there any other final questions that have come in?
No, it looks like we've covered everything, Scott. So yeah, thanks again to you. We appreciate your time and expertise on this matter. And just a reminder to everyone that the recording of today's session will be distributed to all participants along with the post training survey. So please, if you have the time, take the survey and let us know the feedback. It'll also be posted to the Connecticut Passive House website. And just lastly, a reminder that today's training and all the trainings as part of this series are brought to you by the sponsors of Energize Connecticut. So thank you to Energize CT.
All right, thanks everybody. Have a great day.
Thanks, Scott. Take care.